from Dr. Satish Chandra. So with this short break, I would like to welcome you all once again. We can go with our next speaker, Dr. M C Nataraja. At present, he is the professor and the former HOD of Civil Engineering Department, Ramaiah Institute of Technology, Bangalore. Earlier, he worked as a principal, Bapuji Institute of Technology, Davangere. He has served as professor of Civil Engineering Department for 33 years at Sri Jayachamrajendra College of Engineering, Mysore. He is a recipient of ICI Outstanding Concrete Technologist Award for his contribution to cement and concrete technology in India. Sir graduated in civil engineering from SJC, University of Mysore in 1983, securing 8th rank. He obtained his master's in industrial structures from NIT Surathkal in the year 1985 and obtained his doctorate from the Indian Institute of Technology, Kharagpur in the year 1999. The area being fiber reinforced concrete. He has authored and also co-authored more than 300 publications in journals and conferences at national and international level, mainly in the area of special concretes and concrete technology. He has also reviewed more than 150 technical papers to refereed national and international journals related to cement, concrete, and composites. He has many awards and distinctions to his credit by professional bodies, which include Best Technical Paper Awards by the ICI twice, and International Council for Fiber Reinforced Concrete as the Best Engineer Award by IEI Mysore. He also has to his credit the Best Teacher and Engineer Award by Lions Club of Mysore. Dr. M C Nataraja is one of the most distinguished concrete technologists known for his valuable contributions to research, consultancy, and teaching in the area of concrete technology. He is also one of the stalwarts in the analysis and design of structures. His contributions are related to sustainable concrete, utilization of industrial byproducts, fiber reinforced concrete, self-compacting concrete, high performance concrete, geopolymer concrete, soft computing tools in concrete technology, and concrete mix design. In total, he has 34 years of teaching experience, consultancy, and research. He has guided about 75 master's theses and 3 PhD theses on advanced concrete technology and reviewed and evaluated many PhD theses of reputed universities. Sir has delivered more than 300 technical talks to professionals from the government departments, colleges, and industries. He has visited Oxford, London, Japan, Kuala Lumpur, and Dubai in connection with technical conferences and deliberations. Dr. Nataraja has served as subject expert for AICTE, UGC, VTU, and NPTEL, and he is the invited subject expert for educational satellite program of VTU, Government of Karnataka. Sir has also chaired technical sessions in many national and international conferences and served as an advisory and technical committee member for several conferences on concrete technology in India and abroad. He enjoys Google citations of the order 1844 and SCI citations of 1245. The WS core collection citations of 685 till date. He being a stalwart, sir, we welcome for the second session. It's an honor for us that we are here as a speaker for our faculty development program. I welcome Dr. M C Nataraja. Welcome.
Thank you, Professor Niranjan, for your nice words. Respected participants, mainly the teachers from different engineering colleges across the country. I'm extremely happy to be a part of this particular program. The 5-day FDP program being organized by the Department of Civil Engineering at Ramaiah Institute of Technology, Bangalore. As you know, the FDP is on advances in highway technology and traffic systems. And I'm extremely grateful to the first speaker. In fact, I was a bit worried whether I'll be able to give the complete glimpses of what I wanted to share as a part of high strength concrete, especially applied to rigid pavements. But my job has become really simple, that the previous speaker, the professor from IIT, he has covered many aspects of sustainable construction, sustainable materials, especially in the area of concrete making as applied to pavements. I'm indeed grateful to Professor for making my job a bit easy. Teachers, I'll be today introducing to you for about 1 hour the importances of high strength concrete, especially in the area of rigid pavements. How one can design high strength concrete using the sustainable materials, and of course, with and without fibers is what probably I'll be interested in covering. And as you all know that the Indian Standard Code, IS 10262, was silent as far as high strength concrete was concerned. And very recently, the code was revised in 2019. And a lot of input has come to the code, and where that code acts as a guidelines for the design of any type of standard concretes, starting from M25 and going up to M60. I was going through some of the course of practices applied to the pavement, where the high strength was limited to something like 40 megapascal, 50 megapascals, and 60 megapascals. And I have not seen any pavement application where the concrete of strength more than M60 has been used. So probably this M40, M50, M60 may be regarded as reasonable high strength concretes. But if you see the current code, IS 10262 2019, the actual high strength concrete starts from M65, having a strength of 65 Newton per mm square at 28 days and going up to M100. I really don't know to what extent M65 up to M100 is really useful in pavement applications. In fact, I have seen many pavement applications in abroad where very high strength concretes are being used, especially in the precast pavements. So nevertheless, so this concept of high strength concrete itself is quite interesting. I'll be covering initially some fundamental aspects of the materials that are really required and what is the real concept behind the design of high strength concrete. So just by selecting certain sets of materials, it is really not possible to design the high strength concrete, especially M60 and the higher ranges. So we need to have some technology of the materials, what new generation materials that can be used. And as pointed out by the earlier speaker also, today we are using a blend of sustainable materials. So all conventional materials today we are not encouraging because of many reasons. As you all know, it is basically the sustainable materials that really matters. And maybe at the end for about 10 minutes, I'll be introducing to the importances of fiber, especially in high strength concrete, mainly from the point of ductility, energy absorption, capability of the concrete. I will now first show my slide. Just to have a small introduction, use of alternative materials in pavement concrete, mainly from the sustainability point of view. Some of these materials were covered by the earlier speaker also in the first session. You're all aware of supplementary cementing materials. Basically, they are called as mineral admixtures. We have fly ash, slag, silica fume, metacholine, calcined clay. And of course, we have a host of such mineral admixtures being covered in IRC code and also in IS 456, being the basic code for concrete. We also have a host of chemical admixtures, especially the plasticizers, superplasticizers and hyperplasticizers are very, very popular, mainly from the point of enhancing the workability of the concrete, from the point of saving cement or cementitious material. And of course, this chemical admixture is one of the compulsory thing what we are seeing in today's RMC concrete. Also, my dear friends, we have a lot of alternative aggregates, fine and coarse aggregate that are being used in the current concrete. And also, you know that IS 383 published in 2016 speak of many alternatives as a part of fine and coarse aggregates, and use of these materials are really encouraging. And of course, we also have special additives such as fibers. Different types of fibers are there, but I'll be rather interested in telling what happens to the concrete, especially the high strength concrete, when steel fibers are introduced. So the importance of these supplementary materials, to put it in 2-3 sentences, these materials enhance the durability of the concrete. And of course, when that concrete is used in structure, obviously the performance of the concrete structure also gets enhanced. It produces economical concrete and hence economical concrete structures as well. Leads to eco-friendly or the environmental friendly concrete to produce ductile concrete. So to produce ductile concrete, obviously with the help of steel fibers. Now, these are all the host of supplementary cementing materials, and I have taken this figure from the Google, and we will be seeing different types of materials as an alternative to the cement and as a substitution to the part of the cement. These days, people are using these materials. In fact, I already have made a mention of the fly ash slag, ground granulated blast furnace slag, calcine clay, metakaolin, and of course, silica fume. Metakaolin and silica fume are the new generation supplementary materials. We need to use it to the extent of about 10 to 15% in the production of high strength concrete. Otherwise, getting strength beyond, say, M60, M70, going up to M100 plus is extremely difficult with the use of other supplementary materials. So silica fume or metakaolin is a must supplementary cementing material as applied to high strength concretes. Now, if you see what is the importance of ordinary Portland cement in the concrete production, so this is what probably you all must be aware of it. So use of OPC today is not really recommended. And as you all know, production of 1 ton of carbon dioxide leads to almost 1 ton of carbon dioxide. So I have given the split. Of course, we have different process of manufacturing of concrete, manufacturing of cement, I'm sorry. So there is a calcination process which consumes to the extent of about 540 kg of it releases about 540 kg of carbon dioxide to the atmosphere, constituting about 55%. And of course, burning also produces carbon dioxide to the extent of about 35%. And to be precise, around 340 kg. And we also need power, the energy part of the cement production to the extent of about 10%, 90 kg, and all put together close to 970 kg, and that can be rounded off approximately to 1000 kg. So 1 ton of a cement, if you produce it, it releases almost 1 ton of carbon dioxide to the atmosphere. So this is something very large. So it definitely has too much of carbon footprint that need to be reduced. And only the way to reduce this is use of different types of supplementary cementing material and combinations of the supplementary cementing material. Binary blend, tertiary blend, and of course, you can also have the blend of 3, 4, 5 such supplementary materials, and that is quite possible. And in fact, here in this particular slide, again, I have taken this information from the Google, and whatever the property of the concrete you are talking of, especially from the point of fresh concrete, water requirement, workability, bleeding, segregation, heat of hydration, whatever the property in general we are talking of, many of these properties are becoming better. So you can just appreciate some of these things. So many of the requirements of the concrete today, if you see, it is getting improved mainly because of the use of these supplementary materials. And also, if you see the hardened concrete, whatever you are talking of, the strength gain. And of course, some supplementary materials, depending on the quality of the material, depending on the pozzollanicity of the material, sometimes the strength might decrease, but there are instances that if the supplementary materials are of quality type, so definitely the strength, the compressive strength of the material, or even the other related strength, because most of the strengths are primarily related to compressive strength, they definitely increase. Addition of silica fume and metakaolin all the time increases the compressive strength, and that is the reason addition of 10 to 15% of silica fume or even the metakaolin as a substantial improvement in the performance as far as high-strength concrete is concerned. And even the abrasion resistance of the concrete will be better. Drying, shrinkage, and creep will be better with the addition of these supplementary materials. And as many of you must have appreciated that the permeability of the concrete also decreases substantially due to the addition of these supplementary materials, individually or even as a combination. The chemical resistance definitely improves. So as far as the carbonation is concerned, of course, some people have told that carbonation might improve when you have a combination of supplementary materials, but otherwise not much of a problem as far as carbonation is concerned. It is do not have much significance as far as the carbonation is concerned. That's where the arrow is almost horizontal. These are all some of the advantages due to the use of supplementary materials in the production of any type of concrete from the point of hardened properties are concerned. The next important thing which I was mentioning is the use of chemical admixtures. And if you see the American Society for Testing of Materials, the code of practice, the different types of chemical admixtures are permitted, and they are referred to as type A being water reducing admixture, type B retarding admixture, type C accelerating admixture, type D water reducing and retarding admixtures, type E water reducing and accelerating admixture. And in fact, in the current work, whatever the work we have done, in one way or the other, we are using the type F and type G, where type F is high range water reducing admixtures. So these are referred to as super plasticizers or the hyperplasticizer in our country. We also have high range water reducing admixtures. So probably, so these are very, very close to hyperplasticizer, maybe with the accelerating effect or the retarding effect, depending on the situation. So what I want to tell you at this juncture is whatever the course of practices we have in our country, a similar type of course of practices are there even in the West. And if you want to just have a look at some of the Indian course of practices, so it is IS 9103. In fact, I have given the code of practice as far as the ES team is concerned, which I have already spoken just now. And we also have the British code of practice BS 5075 and IS 9103. Whatever the list of the chemical admixtures being covered by ASTM, yeah, more or less a similar type of coverage is there in BS and also in IS. What is important for the Indian research is concerned, so we have different types of plasticizers that are available. It could be a conventional plasticizer or a super plasticizing admixture, which is of a normal retarding type, or just a conventional super plasticizer, or it can be a hyperplasticizer. Use of these super plasticizers and hyperplasticizers, as you know, it is very, very popular in RMC, especially in the production of high strength concrete and high performance concrete. So my dear friends, so now I'll be interested in introducing to the toughness of the concrete. This is one of the property we're all talking of today, especially when it comes to the question of pavement applications. And if you see the conventional concrete where fibers are not used, whether it is a normal strength concrete or high strength concrete, though it is very good from the point of compressive strength, it has its own limitations. Especially the ductility part of the concrete is rather questionable. The energy absorption capacity of the concrete is rather less under all types of loading, whether it is a compression load, tension load, especially in split tension test or in the flexural test, or as applied to wear and tear resistance. As you know, the normal concrete is really not going to perform well because it is highly brittle in nature. And many people are under the impression that as the strength of the concrete increases, many of these toughness related properties will increase. There might be a small improvement in the toughness, but the rate of increase in the toughness, the rate of increase in the energy absorption capacity is not in the same ratio as the compressive strength of the concrete is increasing. So when you take, say, M40 concrete, when it is compared with M20 concrete, the toughness may be slightly better, but not that the toughness of the M40 concrete is increasing almost by 100%. So unless we add some additional materials to the concrete, it is extremely difficult to increase the energy absorption capacity of the concrete. So this is where the use of fibers plays a very important role. And we have the concept of fiber reinforced concrete. and steel fiber reinforced concrete in particular. So the energy absorption capacity, which means more area under the load deflection curve. I really don't know whether you are all aware of the fact that the area under the load deflection curve, especially in flexure, keep on increases as the amount of fiber is increased. And of course, there is aspect ratio and volume fraction coming into picture as these parameters are increased. So definitely the area under the load deflection curve also keep on increases. More area under the stress strain curve. The moment I say stress strain curve, obviously it is the stress strain characteristics of the concrete in axial compression. So that is where the improvement in the toughness, improvement in the energy absorption capability of the concrete. More resistance to abrasion, impact, wear and tear is mainly because of the addition of different types of fiber. But if you add steel fiber, so lot of improvement in these properties, mainly from the point of strength and of course from the point of energy absorption capability. And that is where structurally your concrete becomes better and better with the addition of steel fiber. So what I want to tell you with this addition of fiber, your concrete will become more ductile. Obviously, the failure of the concrete will be rather slow and gradual. So it is not an instantaneous type of failure. It is not a catastrophic type of failure. So that is where you should be very, very happy to have these steel fibers being introduced into the concrete. Obviously, add fibers to concrete so that many of the performance characteristics of your pavement increases. Now, this is one of the interesting the behavior I want to share with all my teachers. So this is where the load deflection characteristics, this is a schematic diagram. So what I want to just tell you, so probably in all the compression testing, we are interested only in one particular point. So though the horoscope of the concrete, the entire behavior of the concrete, the ascending behavior, and of course you also have the descending behavior, how much is the area under the curve, what is the area under the ascending part of the behavior, and what is the area of the descending behavior. Many of these things plays a very important role, especially when you want to characterize the concrete from the performance point of view. But otherwise, what we normally do is we test the concrete cube, the ultimate load divided by the area. So that is where the compressive strength of the concrete, that is really, really important from the point of characterization of the concrete with respect to its grade. But without knowing the real distribution, the real area under the curve, the load deflection diagram or even the stress strain diagram of the concrete, it is really, really not possible to define any performance characteristics. Now to this plain concrete, kindly see, if you add fibers at some rate, of course, I will come to that in a short while. The area of the ascending part also gets modified, which we will be discussing later. And the load carrying capacity also will increase marginally. Please keep it in mind that if at all I am going to add steel fibers to concrete, it is not to increase the compressive strength maybe by about 2, 3, 4 MPa or 5 to 10 MPa. What is important is to appreciate this drooping behavior of the concrete. Whatever the area you are going to get now because of the addition of the steel fiber, that is quite tremendous. So this is many times more compared to the area under the drooping part of the normal curve. So drooping part of the plain concrete of the normal concrete. And if you are testing the concrete with conventional testing machines, so generally they are called as the mechanical testing machines. So in mechanical testing machine, we have only the rate of control of the load possible, but we really do not have any control of the deformation to be exercised or even the strain deformation or even the stroke. So many of these control is really not possible. And definitely in a mechanical testing machine, we will not be able to trace this stress strain diagram or even the load deflection diagram in case of flexure. So we really need the Instron machine or some sort of a MTS machine. They are all the higher end machines. And with that machine, it is really possible to trace down not only the ascending part and even the descending part of the behavior. So with this, the area under the curve and what is the drooping area. So once the ultimate load is reached and in the softening part, how much of area that is being occupied by the stress strain diagram and what is that as a ratio to the ascending area. Many such properties will be able to determine and thereby the ductility characteristics of the steel fiber reinforced concrete, energy absorption capability of the steel fiber reinforced concrete. Many of these can be defined and full characterization of the material is really, really possible. Hope you are understanding all these things. And also we have a concept these days, instead of adding just half a percent of steel fiber or 1% of steel fiber, generally steel in excess of about 2% is really not permitted because of many of the problems. As you know, it could be the balling problem or it could be the workability related problems. And to some extent, because we have new generation chemical admixtures that are available, we'll be able to satisfy many of these properties, but steel fiber excess of about 4% is extremely difficult. But you also have a concept called as slurry infiltrated concrete, where 10, 15, 20% or even beyond the fibers can be added to concrete. The only thing is kindly see the behavior of the SFRC. That itself is far, far better compared to plain concrete. But if you see the area now under the curve, it is substantially increasing much more. It's all because of the additional the benefits given by this slurry infiltrated concrete. I'm not going into the details because it is not under the purview of my presentation today. And also we have the concept of new generation SFRC, where different types of steel fibers, different combinations of steel fibers are added, and the area under the entire curve is now modified. Now kindly see what is the ductility part. What is the energy absorption capability of the concrete? It is many, many times compared to even the steel fiber reinforced concrete, and that itself has got tremendous advantages when compared to the plain concrete. And of course, you also have a new concept called as compact reinforced concrete. So this is actually the research topic, and a lot of research is going on in this particular area. You do find many, many technical papers at the international platforms. The compact reinforced concrete, probably if you take a beam, we will be putting a higher percentage of steel, much more than what is permitted by the IS 456. IS 456, probably, as you know, 4% of fiber at the compression and tension put together is about 8%. But this is the compact fiber reinforced concrete, where steel in excess of 8% and sometimes going up to 12% of steel as a rod we will be putting, not only in the tension part, even in the compression part. So in that sense itself, your concrete beam is far, far better. But to that, if you are adding steel fiber, I really don't know. So what will be the behavior of such a type of composite? So that is where I have just shown a small part of the ascending behavior. Kindly see the ascending behavior. You will go something like this. Schematically, I'm trying to explain. And if you try to extend it further and further and further, please look at the cursor, the way I'm taking it. It will be going substantially above and substantially far away. Means that most of these diagrams will be well within the diagram, whatever I am mentioning as a part of compact fiber reinforced concrete. So whatever you find here, slurry infiltrated concrete or new generation SFRC or even the compact reinforced concrete, lot of research is going on at present, especially when you bring in new generation cementitious material, supplementary cementing material, new generation mineral admixture, and of course today we have lot of nanomaterials that are coming into picture, and with these combinations, so wonderful research can be done in this particular area of high strength, high performance, new generation concretes. Now, just a few words connected with fiber, because today fibers are also being used. IS 10262 published just a year back is a bit silent about the use of fiber. But if you see the IRC code meant for concrete mix design, so steel fibers are permitted. In fact, we have already published several papers available in the Indian Concrete Institute journal. So just a couple of months back, so one of the paper has come there. And there are several papers in this particular direction in the international platform. So you can just refer and get to know what the advantages of some of these fibers. The fiber which we have used in our work is looking something like this. So it is steel fiber. So it's some sort of an undulating steel fiber, but otherwise we have many forms of steel fibers as you can see here. These are some of the diagrams I have taken from the Google just to tell you that the fiber means not just one type. There are several types, and there are several parameters of the fiber that comes into picture, and otherwise it is really not possible to define the performance of the concrete. It's not just one parameter. Aspect ratio of the fiber comes into picture, that is L by D. What is the length of the fiber? Equivalent length divided by the equivalent diameter. And as the aspect ratio increases, of course, the mechanical properties of the concrete might increases. But other related properties, especially from the rheological point of view, the workability and other things might decrease to some extent. And how much of fiber you're adding is another question you need to ask. That is where the volume fraction of the fiber comes into picture. As the volume fraction of the fiber increases, many of the mechanical performance of the concrete increases. But as I mentioned, the workability of the concrete decreases to some extent. But for the first time, if you see in the literature, the volume fraction and the aspect ratio, both were considered together as a multiplication factor. And we have introduced one concept called as the fiber reinforced index, L by D into VF for the first time. So this concept of fiber reinforced concrete has been introduced, and there are several papers which we have published almost 20 years back in this particular concept. And today it is the fiber reinforced index concept from the point of concrete mix design, where the importance of both aspect ratio as well as the volume fraction of the fiber are considered in the design of steel fiber reinforced concrete. Also, we have the concept of critical length. Certain minimum length we have to have. Anything less than that, it is really not going to serve the purpose. It acts only as a filler. But if the size is more than the critical length, where that critical length obviously should be minimum 1.5 times the size of the aggregate. If you are talking of, say, 10 mm aggregate, and if your fiber length is less than 10 mm, probably it is not going to contribute much to the aggregate part. It might increase some properties of the mortar of that particular concrete, but concrete as a composite, probably the performance is not going to increase. So that is where selecting certain minimum length, depending on the size of the aggregate, plays a very important. So any fiber in excess of about 2%, we have the balling problem, and we need to go for a concrete, good concrete mix design. Many such things comes into picture, because in the current IRC, fibers are permitted unless you know many of these things, mainly from the point of mixed design. Producing a very good steel fiber reinforced concrete may not be that easy. So types of fiber, size of fiber, shape of fiber, strength of fiber, modulus of fiber also play a very important. So what is the meaning of strength and modulus? As the strength of the steel increases, strength of the concrete increases. As the modulus of the fiber increases, the modulus of elasticity of the concrete also increases. But if you see, there are many instances the students have used the polypropylene fiber, nylon fiber. So they are all not high modulus fiber. And also if you take the compressive strength or even the tensile strength of the fiber, it is not that good when compared to steel fiber. How do you expect the mechanical properties of the concrete to improve? So definitely not. So ductility part can improve. The energy absorption capability, especially in the drooping portion of the stress strain diagram, can be a better thing, but otherwise the compressive strength of the concrete is not going to increase. The mechanical properties of the concrete is not going to increase, especially when you go for low modulus fiber or the fibers which are of low strength when compared to steel or carbon fibers. So this is just a small introduction, because today these types of fibers are also being used in the pavement concrete. And one more important point from the advanced concrete technology point of view, because today many of you must have studied this concrete technology, a basic subject, advanced concrete technology. And today advanced concrete technology of new generation material is what many people are talking of at the Now kindly see, this is actually the microstructure of the hydrated cement paste. Hydrated cement paste consisting of OPC only. What probably you need to see is this CSH gel. So this CSH gel, kindly see the volume of the concrete, what I am taking at the micro level. So this is the micro level area. In that area, if you see, how much is the distribution of the CSH? Calcium silicate hydrate gel. This is actually the strength forming compound. It really adds to the quality of the concrete. It adds to the strength of the concrete. When the OPC hydrates, we also should know that there is calcium hydroxide being liberated. So this calcium hydroxide is not a good material. It reacts with carbon dioxide and further reacting with carbon dioxide. So you have calcium carbonate and calcium bicarbonate, which leaches out of the concrete. And because of this, the concrete becomes more porous inside. So that is where the durability of the concrete over a time becomes questionable. So we need to decrease this calcium hydroxide, but as long as you have OPC alone to the extent of 100% in your concrete, so it is extremely difficult to avoid this calcium hydroxide. So this is really not a material required from the point of durability. And also, if you see, we also have one more important box compound, especially the calcium aluminate. Though we keep the calcium aluminate less than about 10%, and this calcium aluminate, along with some of this sulfate compounds, because many a times the concrete will be exposed to the marine environment. And in fact, we have the acid attack coming into picture. We have the sulfate attack coming into picture, and different types of sulfates reacting with gypsum. And of course, with calcium aluminate, over a time, we get a material called as ettringite. So this is a sort of mineral. So this is one material responsible for the lack of performance, the lack of durability related performance, especially in your concrete. So this is what is referred to as calcium sulfoaluminate, which is really a detrimental material as far as ordinary Portland cement is concerned, ettringite. And of course, ettringite can form immediately, or it can even form over a time, depending on the situation. My dear faculty, what I would like to tell you is, when you make a concrete today, don't use 100% of cement. In fact, since 10 to 15 years, people are not using 100% OPC, but still, I'm seeing many applications where 100% of cement is being used. But we need to replace certain percentage of OPC, say to the extent of 25%, going up to 50% with some of the supplementary cementing materials. But if you take slag, for example, ground granulated blast furnace slag, there are instances that researchers have used to the extent of 75% and going up to 90% slag, maybe just 5% of clinker, and maybe another 3 to 4% of your gypsum, they are getting super sulfated cement. So one of the best possible cement from the durability point of view. And in fact, this super sulfated cement is also recommended in IS 456, and that is where the application of high volume fraction of slag comes into picture. And we also have high volume fly ash concrete, very, very popular in the West, but as far as our country is concerned, maybe to the extent of about 25 to 30% is being used in the blended cement. And of course, we have some RMC applications where slightly in excess of 30%, maybe going up to 40, 45%, still I'm saying, but definitely not more than about 50% of fly ash in any of the concrete applications. And one more important thing, what I would like to tell you, especially from the point of high strength concrete mix design, because I have seen people simply modifying the composition of the concrete, simply modifying the combinations of the supplementary material, and how these supplementary materials are really contributing to the enhanced strength of the concrete. So that you will be able to make out only when you see the scan picture of the concrete. Here I am showing you the microstructure of the transition zone. Kindly see here, this is a pictorial representation. It is a sort of schematic diagram only to get a feel of how this high strength concrete can be really designed. Now this is actually the coarse aggregate, as you can see here. And this is actually the matrix. So the hydrated cement particle. And kindly see whatever the product just now I mentioned, calcium hydroxide, which is in the form of a crystal, calcium silicate hydrate, the one which gives the strength, and of course, the ettringite, which is really not required, so which is detrimental to the performance of the concrete. So these are all the materials. But if you see what is the material that is available very close to the aggregate. Now kindly see, have a look at this particular picture, and we have more of calcium hydroxide available. We have more of ettringite available, which is very close to the aggregate. What the aggregate is embracing is not the strength forming compound. In fact, the strength forming compound is substantially away from the aggregate phase. Now, what is the phase I am talking of? It is not even 1 mm. It is just 0.1 mm. And that is where the importance of the transition zone, especially in the high strength concrete mix design, comes into picture. Now, if you see here, the transition zone is just 10 to 50 micrometer in thickness. This is what the transition zone in terms of mm, it is 0.01 mm going up to 0.05 mm. And that is what the zone which is holding the aggregate, and thereby the bond strength of the concrete is getting increased. It is not just the material, it is not just the strength of the material, at some point in time, especially in case of high strength concrete, what is the load that really breaks the aggregate from the rest of the matrix? So the transition zone and its strength. So I want to bring whatever the material which is away from the face, that calcium silicate hydrate gel, that has to come rather close to the aggregate. For that to happen, I need to see that whatever the calcium hydroxide that is available, which is very, very close to the aggregate phase, that has to eventually react with the supplementary cementing material. So many of these supplementary cementing material, my dear faculty, it contains silica, it contains alumina. And whatever the calcium you find here abundantly, that eventually reacts with the silica and we get calcium silicate hydride. It eventually reacts with alumina, you get calcium aluminate hydride. They are the two strength forming compound depending on what type of supplementary cementing materials you are using. So what the condition you have substantially away from the micro zone, the transition zone, the same future you will be bringing in to very close to the aggregate phase. And that is what the good phase, the strength phase, which is embracing the concrete. So with this, the compressive strength of the concrete increases to the extent of about 30, 40, 50 megapascal. So this is what we have seen in many of our research. And one more interesting thing, which I have taken from P.K. Mehta textbook, kindly say here, the relationship between the stress strain of the individual ingredients I am giving here. Of course, the aggregate is a linearly elastic material, and of course, the strength increases. The modulus is more or less constant. And you can see even the paste also, it's also linearly varying. Modulus of elasticity is constant. So you can call these two materials having a Young's modulus, linear elastic properties being exhibited. But otherwise, your concrete is elastic, but my dear friends, it is not linearly elastic. There's no Young's modulus you can define as far as this concrete is concerned. And we have different definitions of modulus that is coming as far as concrete is concerned. Now, what I want to tell you is when you add this aggregate and the cement paste, we have the concrete. And what the performance of the concrete you are going to get is in between that of the aggregate and the cement paste. And this is very, very clear. So you will never be able to bring the quality below that of the paste unless the mix design is very poor. And at the same time, whatever the way you do the concrete mix design, you will never be able to bring the behavior of the concrete much closer to the y-axis, much closer to the, what I can say, the aggregate. It is extremely difficult because of the very poor quality of the cement paste. How to increase the quality of the cement paste is the question now. So that is where the low water cement ratio of 0.2, 0.25, 0.3 with supplementary cementing materials. So probably this line itself, I can push it towards the y-axis. And at the same time, if you go for a good quality coarse aggregate, today lot of unconventional materials are coming up. That is where the steel slag far better compared to your conventional aggregate. I'm very sure that this behavior can be still pushed towards the y-axis and cement paste behavior can be further pushed and the concrete behavior becomes far better, which you'll be seeing in the next slide. Kindly say what is really going to happen. This is what, if you have a conventional material of any quality, but this is what the material I'm looking from the current research. So definitely I'll be able to push my line, stress strain line, whether it is linearly elastic or non-linearly elastic towards the y-axis, and my initial curve, the stress strain diagram, whatever I have, so that will become something like this. So with this, any property of the concrete, the modulus of elasticity, the secant modulus, the Card modulus, whatever you are talking of, it will be definitely be better compared to that of any conventional concrete. So keeping this concept in mind, if you do the concrete mix design and getting M60, M70, and even M100 plus concrete with the materials that are available in the Indian context, it is really possible. So that's what I just want to share as a part of high strength and very high strength concretes of our country is concerned. And also one small thing I would like to tell you, this is where some debate of water cement ratio comes into picture. I'm not going to take much time here. So the water cement ratio in excess of 0.55 is really not permitted by the Indian code, IS 456-2000 being the mother code of India. Why it is so, and why we can't go for a concrete of 0.6 or 0.7. But in the Western countries, higher water cement ratio is permitted. What is important is to say that the concrete is impervious to water, impervious to chlorine as an ion. It is impervious to all sorts of ingression. But as far as water is concerned, so definitely when it evaporates, so certain amount of internal defects in the form of a capillary or in the form of a void will be introduced into the concrete. And that is the problem. But when you start using supplementary cementing materials along with the cement, even with 0.55, 0.6 and 0.7 water cement ratio, my dear friends, and if you see these strength ranges, 2000 to 3000 PSI. This is what the graph I have taken from the American Concrete Institute 211 code, which is available in the internet. And kindly see that 3000 to 5000 is nothing but concrete having a strength of 20 to 35 Newton per mm square. But why in the Indian context, our people are struggling to get even M20, M25, and why they are simply putting water, and with that water, they are not able to get the compressive strength because they are not putting the supplementary cementing materials. So they want to produce the concrete only with OPC, and that is the reason. So when water becomes more and more, where the water cement ratio is exceeding beyond 0.5, going up to 0.7, so our concrete is definitely vulnerable. But with the combination of the supplementary materials, so your concrete will be substantially better in terms of strength. But if you see in the next slide, kindly see, the moment you start using the supplementary cementing materials, some combination of SCM1, where I have tried with fly ash, and maybe the second one with slag, some combination of fly ash and slag as a ternary blend, kindly see the amount of charge that is passed when you are conducting a rapid chloride permeability test. This particular service at present is available everywhere, and every laboratory is having this facility. And kindly see, even at a water cement ratio of 0.7, not permitted by the Indian code, you are able to get a concrete whose charge passed, the Coulomb value, which defines the impermeability of the concrete, is close to 2000. What is the 2000? If you see in the rating that is being given by the ASTM, it is a very, very low rate of charge being passed. But otherwise, if you go only for ordinary Portland cement, even at a water cement ratio of 0.7, see, my dear friends, your charge will be very close to 7,000 to 8,000, means it is a highly impermeable concrete. So if you want to make your concrete permeable, you have a concrete, you have a mixed design, everything is being defined, but replace some 25% of the cement, 50% of the cement, buy the supplementary materials, quality supplementary materials, bring down to binary blend, ternary blend, and with that, so your rapid chloride permeability. So that decreases tremendously, and where your concrete is having a very low permeability. And many of the studies which you have done in the recent past, our RCPT value is very close to 100 to 200, indicating that our concrete is almost close to some sort of a polymeric concrete, epoxy concrete, highly impermeable concrete, and that can be regarded as a metal concrete. And today people are talking of metal concrete, where my concrete can be compared similar to that of a metal from the point of permeability. Now, these are all some of the important things you should know before you venture in designing high strength concrete or even the high performance concrete, especially M60 going up to M100. At present, the Indian recipe is available, and anything beyond M100 is also quite possible. And of course, you also have a very interesting code released by the Bureau of Indian Standard, IS 383. 1970 was the earlier code, where only the natural river sand was permitted. But today, if you see, so we have a host of such aggregates that can be used as a fine aggregate and also as a coarse aggregate. And I'll be just showing you one slide, which is really not encouraging. If you ask me as a concrete technologist, I really don't agree with what Bureau of Indian Standard has suggested at present. Indian Standard is suggesting just 20 to 50% of the replacement of regular aggregate with unconventional aggregate, that too in the plain concrete. So that is where these red values, not so encouraging. But if you see, in case of RCC, not even to the extent of 25%, the Bureau of Indian Standard is recommending. So now it is high time for BIS also to come out with some new documents based on the research information available in the at the Indian context, and also taking some of the international references. 100% of these types of unconventional materials should be recommended. And if you see many of the technical papers which we have published over a time of 10-15 years in the past, they are all with 100% replacement of the aggregates. And of course, we also used some 20, 40, 60% just to tell you where exactly certain parameters will become optimum. But otherwise, even if you use 100% of the aggregate, you may be having a problem of workability. Increase the workability with the admixture. You may be having a problem of compressive strength. Decrease the water cement ratio, decrease the water, and see that a slightly higher percentage of the chemical admixture is exercised. With that, your workability is satisfied. Your lower water cement ratio, definitely according to Abraham's law, your compressive strength increases only with mineral and chemical admixture. By using any type of unconventional aggregate and any combinations of unconventional aggregates. So today we will be able to produce M60 going up to M100 concrete with the available resources of our country. And this is what even the earlier speaker was making a mention. Many of these unconventional aggregates, we need to bring into the concrete mix design. We have already brought it, but now it is only the awareness we have to bring in with the stakeholders so that people can come forward for using many of these alternative materials and their combinations to produce sustainable concrete. Now, finally coming to the mix design. The studies on high-strength concrete IS 10262 2019. So my dear friends, I'm not going into the greater details of what the concrete mix design, because you are teaching this particular course to your undergraduate students also. So I will just tell you in a nutshell how one can design the concrete, taking all the information, whatever I have discussed so far, so that some good information can be looked at from the mix design point of view. And we have taken up a very simple work. So I'm just taking one combination of supplementary materials. I have used GGBFS to the extent of 50%. Silica fume, without silica fume, it is not possible to produce the high strength concrete. Otherwise, you may have to use the metacholine to the extent of about 10 to 15%. So 65% of supplementary materials and only 35% of cement we have considered here to produce concrete up to M100. And also we have the PCE based admixture, polycarboxylic ether based admixtures. It is a new generation admixture, works on the principle of steric hindrance. It's not working on the principle of what I can say, electrostatic repulsion. Electrostatic repulsion is a concept being generally observed in plasticizers. And today we have a high molecular weight based polycarboxylic ethers and esters with steric hindrance concept, wherein about 0.25% of admixture. Maybe to make things clear, just half a liter of chemical admixture, where you will be able to remove about 30 to 50 liter of water. Instead of making a concrete from 190 to 200 liter of water, you need only 130 to 150 liter of water, my dear friends. Just 150 liter of water. I am replacing 30 to 50 liter of water, but I'm only putting half a liter of hyperplasticizer. So half a liter of hyperplasticizer costing about 200 to 300 rupees is equivalent to reducing 30 to 40 liter of water. Means that your water cement ratio has drastically reduced from say 0.6, though not permitted, 0.55 permitted, to as low as 0.3, and of course very close to that. Thereby the concrete is definitely M60, and of course even a higher order of strength can be designed. And of course we also tried with steel fiber, so as another work where some ductility part of the concrete can also be appreciated. So there are 9 steps in the mix design, which is already known to the faculty. Since you're all the faculty, I'm not going into the details as to what this mix design is all about. And of course, M65 to M100 is what the concrete mix design being covered. High strength concrete means 65 and above only, as far as the current code is concerned. And we have used 269/2015, again the latest code, where 53 grade cement is permitted, silica fume with a specific gravity of 2.05, and GGBFS with a specific gravity of 2.83, and 70% of the bigger aggregate, 20 to 10 size, and 30% of the lower size, 10 to 4.75. Sand is zone 2, recommended for strength concrete, and as I mentioned, polycarboxylate ether being the hyperplasticizer. I'm just showing you one mix design table. So this we have got it by developing it in Excel platform. We have different platforms to do the mix design. I have used the Excel platform. You can also use any other platform depending on your interest, so that you will be learning this soft tool also. And kindly see M65 going up to M100. The water cement ratio is 0.31 going up to 0.1. Getting a concrete at 0.31 water cement ratio, even with 0.5 water cement ratio, your concrete is not workable. How can your concrete be workable with 0.31? So that is where the use of superplasticizer, that new generation superplasticizer comes into picture. And as you decrease the water cement ratio, as the grade of the concrete increases up to M100, so you need to use slightly higher dosage of such hyperplasticizer being permitted by the latest course of practices. And also kindly see the cement. The cement is 202 going up to 450. Kindly see 446 means I have ensured the requirement, what the code is telling. So the cement content should not be more than 450 kg, but not the cementitious system. Cementitious system means cement plus silica fume plus GGBFS. So when you add all these things, probably it might cross 450 suggested by the IS 456. But mind you, IS 456 is not the code meant for high strength concrete. It is only for the standard concrete. As long as you have the standard concrete, yes, the cement content should not be more than 450 kg, minimum being 300 kg. And even with that 300 kg minimum, I'll be using only 100 kg of cement, my dear friends, 200 kg of supplementary materials, but 300 kg of cementitious material. We have given enough of concrete mix design to the stakeholders for M20 to M25 grade of concrete. But here, so the cement content is 300 going up to 450 with some combinations of GGBFS and silica fume. So total yield very close to about 2,400. Any grade of high strength concrete can be designed. And in fact, the recipe is available at present in the current code. And it is in fact a boon to our Indian researchers. The same thing, I have put it in the pictorial way. So you can just appreciate. I'm leaving the PPT also for your reference. Maybe you can just go through it whenever you have the free time. And you can get back to me or a phone, or you can even send mails to me so that I'll be responding to your queries for a time. And of course, we need to do the trial mixes. Without trial mixes, your mix design is not going to be completed. In fact, I have seen in many of the engineering colleges, they do only one mix design and finally they recommend the mix design, but we need to go for a trial mix. What is trial mix? So this is where keeping the water constant and changing the water cement ratio by plus or minus 10%, we need to work out two additional concrete mix for any concrete mix design for that matter, so that economic constraints can be exercised in your concrete mix design. Yesterday time? No, 10 minutes. Okay. Now kindly see here, I have put some information here. If you are designing an M70 concrete, this is the first trial mix, what you get it from the first trial. And anyway, you have the computer program where the additional trial mixes can be exercised. And based on the result of the first trial, we will be doing the mix design of the trial 3 and 4. This has to happen inside the concrete laboratory. And of course, kindly see the water cement ratio. In the first case, it is 0.29 plus or minus 10%. And for M80, the first water cement ratio is 0.26, what I get it from the basic mix design. And with plus or minus 10%, the two water cement ratios I will be having. And kindly see the increase and decreasing in the cementitious system. And all these things we need to again observe in the form of a graph. And also you need to develop what is called as the water cement ratio graphs to appreciate what exactly the variations that are likely to come. And kindly see, we have designed for 70. 75 mm was the target slump, but we are really not bothered what is the slump of concrete. Even if it is 50, we are not going to bother because we slightly increase the admixture dosage and we get the 75. By chance, if it is 100 mm as against 75, we need to decrease the dosage of the admixture so that any target value of the workability can be achieved. And this is not a design parameter as far as our work is concerned. So any change, I can adjust it because I can change the dosage of the admixture. And kindly see the compressive strength. It is quite appreciable at 3 days, 7 days, and 28 days. I have put it here. Kindly see So 59, 68, 79, and 90, as far as M70 concrete is concerned. At 28 days, I'm getting 79. What I'm expecting to get is just 70 plus T plus S, standard deviation times the statistical value, that extra component to take the difference from lab to the field. That is where about 6 MPa of extra I'm expecting. 76, probably I would have been happy, but it is slightly more than 76. I'm getting about 79, rather close to what I wanted. So I'm not doing any further change. As far as M80 concrete is concerned, I need about 86. So I'm getting about 88. And kindly see at 90 days, it is a marginal increase in this strength. And one more important thing, especially for the teachers, I'm sure that the teachers are aware of this particular fact. The strength what you are going to get at 7 days in comparison with the grade, almost about 90% of the expected strength you get it at 7 days itself. So this is the beauty of the high strength concrete. Now, if you take the conventional concrete, say 30 Newton per mm square, we get about 20 Newton per mm square at 7 days. It is 2/3, means the remaining 1/3, the remaining 33% of the strength you get it from 7 days going up to 28 days. But unfortunately or fortunately, in high strength concrete, you get almost 85 to 90% of the strength, almost equal to the grade. Kindly see, I want M70, I'm getting much more than the grade. I want M80, I'm getting much more than the grade at 28 days itself. And that is what the beauty of high strength concrete. And this is where hardly 10% of the strength I'll be expecting from 7 days to 28 days. Now, what is important is to cure the concrete for the first 7 days. And if you are not curing it for the first 3, 4, 5 days, and then later curing even for months together, you are not going to get the good strength. So this is one important point I would like to share with all of you. And the same thing, I have put it in the graphical manner. Yeah, and even the split tensile strength. So kindly say, as the days age is increasing, the strength is also increasing, and all the equations that are there in the course of practices, so they are being followed. So seeing is believing. So the variation of split tensile strength, and kindly see the nature of the failure when you crush a concrete cube or a prism cylinder. Kindly see there is no debonding of the aggregate happening. Means that all aggregates are cutting across. Means that the aggregate has really contributed to the strength. There is no debonding. This is where the importance of the transition zone comes into picture. Transition zone is so strong, it is able to hold the aggregate. It is embracing the aggregate completely. So this is where the importance of high strength concrete comes into picture. And compressive strength for 10% increase or even 10% decrease. So you can see, and finally you can draw a graph and you can appreciate. So this is what the final graph that is very, very important from the point of subsequent concrete mix design. And even now, using the same set of materials, even if you want to design an M50 concrete or an M60 concrete, so determine the target strength and pick up the water cement ratio, either for the 7-day requirement or even for the 28-day requirement. And your further concrete mix design will become very, very easy with these graphs being developed. So all these things we have published in the Indian Concrete Journal and Indian Concrete Institute Journal very recently, and you can have a look at those technical papers and that will give you the first-hand information. A similar type of exercise we have done it for M80 concrete as well. So now this will become the input for the concrete mix design for your subsequent mix designs. Of course, you also have done some NDT test from the point of quality assurance. So this is where the ultrasonic pulse velocity. Kindly see the range as per the Indian code 13311 is concerned. So 3,500 to 4,500 is a very good concrete. And this is the rebound hammer value. And kindly see our ultrasonic pulse velocity value. 4,000 to 4,500 is what the expected range, but we are getting more than 4,000, indicating that all our high strength concrete, whether M70 or M80, they are satisfying the requirements of the quality as far as the course of practices are concerned. And even the rebound values are quite encouraging. So these are all the remote numbers, but the actual compressive strength is what we have seen by testing. But one thing I would like to tell you at this juncture, so your rebound hammer is not applicable for high strength. And in fact, even if you see that graph itself, there is a limitation. Anything beyond M70 is not recommended, but your graph only gives you the strength as 50 to 56 based on the observed value of the rebound number, but otherwise your actual strength is much higher. It is not only with M70 and even with the M80 concrete. The conclusion from this is your rebound hammer is valid only for the standard concrete, say M20 going up to M50 grade of concrete, anything in excess of say M50. So you have to be very, very careful in interpreting the results. Your rebound hammer says that the strength is less, but your concrete strength may not be lower. So this is where the importance of certain things comes into picture. Now, rapid chloride permeability test, we got it done from the civil aid. And this is the range, as you can see here. But any concrete, if you test it, it will be very close to 1000 to 2000, indicating that the permeability is low to moderate. But because of we exercising higher percentage of supplementary materials, and also because of adding silica fume, so our rebound value is coming, our RCPT value is coming very close to 62 to 100, indicating that it is a highly impervious concrete. Also, we have done the abrasion test, and I will share you the result. For M30 concrete, the wear and tear, what you are seeing on the surface for a given operation of the testing, it's about 0.5 mm. But when it is M70 or M80 concrete, the wear and tear is also quite less. To the extent of about 40%, the wear and tear resistance of the concrete can be enhanced. The average wear, in fact, decreases. So this is where appreciation of the wear and tear resistance, again, one of the important contribution, important requirement for a pavement concrete is also being exercised in our studies. And of course, we also have done the microanalysis. I'm really not aware whether many of you are familiar with this microanalysis. What probably I can tell you is if you have a M30 concrete, this is the aggregate and this is the cement face, and you can see some sort of a light distribution of this structure. There exists as if there is a small gap at the micro level, under the nano level. But when you see for M70 concrete, that gap is densified. And similarly, if you see in the M80 concrete, that densification is really becoming denser and denser at the micro level and the nano level. This only indicates that the transition zone, which I was referring to in the high strength concrete, it is really becoming better, and thereby the bond characteristics of the concrete, especially between the aggregate and the cementitious system, is many a times better. And that is where the improvement in the strength properties, and that is where the improvement in the performance characteristics of the concrete comes into picture. And just to tell you, it's the same mixed design. In fact, we have just added the fiber at different proportion. And this is where the workability decreases. In fact, if you add the fiber, still I'm getting about 40 against 75. But now we should put 0.25, additional 0.25 dosage of chemical. Again, your workability will increases to something like 75 mm or so. And as the steel fiber increases, so kindly see the strength of the concrete also increases, the flexural strength. Today, the pavement concrete is to be designed for the characteristic flexural strength. It is not the characteristic compressive strength. That also we have done it in our work. Depending on the range of the flexural strength, we can do the mixed design. So 0.5% of fiber and 1% of fiber, the flexural strength is increasing. But mind you, if your idea is only to increase the flexural strength, don't add fibers. We need to decrease the water cement ratio and get the increased flexural strength. But in addition to the flexural strength increase, we are getting many of the other improvements, especially from the point of energy absorption capacity. If that is the only requirement, I suggest you to put the steel fiber. Otherwise, don't put the steel fiber just to get some increase in the compressive strength or the flexural strength. And this is what the relation probably you all need to appreciate. And this is the setup which you have used in our laboratory. And this is what the behavior for the normal concrete, my dear friends. The moment you add the steel fiber, the drooping behavior is becoming like this, and tremendous area under the drooping portion. That is where the enhanced ductility, energy absorption capacity. And these are all the typical graphs which you have got it for M70 and M80. And kindly say for M80, the area under the curve is definitely increased, and that is where the toughness of the concrete. And again, for 1% fiber. So this is for 0.5% fiber. If you are happy with the toughness, limit to 1%. If you still want an enhanced percentage of the fiber to be added, so your area is further increasing. And all these area calculation, you can do it because we have the tools available at present, and the ductility of the concrete can be determined. And as I mentioned, kindly see the increase in compressive strength. In fact, the compressive strength is decreasing marginally for 0.5%. For 1%, a small percentage of increase. What it means, the addition of steel fiber need not increase the compressive strength. It can increase marginally, sometimes it can decrease, but mind you, that is not the idea. The idea is only to increase the area under the car, unless these things are looked at from the point of mixed design. So there's no point in you simply adding the fibers. So my dear faculty, so coming to the end of my presentation, I have only 4 general conclusions. Characterization of aggregates and cementitious material from the point of design and from the point of performance is a must. Otherwise, we will never be able to get high-strength concrete. So today we have a code IS 10262, and of course, it's a boon to all the stakeholders, especially the civil engineers and the researchers, where different types of special concretes. Ordinary concrete, standard concrete, high-strength concrete, self-compacting concrete is also being covered. Mass concrete is being covered in this particular code. Of course, we need to use combinations of minerals and chemical admixtures. Use of mineral and chemical admixtures today is a must from the point of durability, because IS 456/2019 is a durability code and it is not a strength code. And what you see in the days to come, it is a performance-based code. Obviously, today we need to take performance into consideration in the design of any concrete, including pavement concrete. Use of crushed aggregate and M aggregate, what the earlier speaker also mentioned from the point of sustainability, need to be encouraged. Here, the concrete, what I have considered for the study is quite durable, eco-friendly, sustainable, and hence most suitable for the rigid pavement application. I'm extremely happy, my dear colleagues. And if you have any questions, you can ask. We can have some discussion for about a few minutes before I close. And I take this opportunity to thank my coordinators, the HOD of the Department of Civil Engineering, and all my colleagues for having chosen me as one of the speakers for this 5-day FDP program. Thank you very much, and I wish you all the best. Have a good time. And now the platform is open for the discussion.
Sir, we have a question in the chat box regarding fiber reinforced concrete. You are told about the critical length, but is there a critical diameter to be considered?
Yeah, there are a good number of questions which I'm able to see in the chart, and I'm very happy to take the first question. Of course, there is what is called as the critical length of the fiber, which I have spoken. Is there anything called as the critical diameter? Probably that's what the question one of the participant is asking. As I mentioned, we have 2 parameters to be looked at. One is the aspect ratio. Without aspect ratio, we will not be able to characterize the concrete. What is this aspect ratio? It is the ratio of length of the fiber to the diameter in a general sense, but otherwise it is the equivalent length as an image to the equivalent diameter, where even if the cross section is rectangular, what is that rectangular area equal to pi d square by 4, and get the equivalent diameter and get the equivalent aspect ratio. So equivalent aspect ratio is a very, very important thing. And any aspect ratio less than about 50, we are not going to get any better results. It's already available in many of the textbooks and the literature documents. And similarly, any aspect ratio in excess of about 100 is also not recommended, even though people have tried with 120, 130 like that. 60 to 80 is an acceptable aspect ratio for any concrete application. So your length and diameter is already considered in that aspect ratio. Now coming to the fact, you can have an aspect ratio of 60, but your length can be small. Now, if you take a 1 mm diameter of a fiber, like your pin, that can also be used. But if you have something like 40 as the aspect ratio, the length of the fiber should not be less than 4 mm. 4 centimeter. That 4 centimeter will become a very long fiber. It causes a lot of problem from the point of congestion, from the point of balling. So that is the reason we need to decrease the diameter of the fiber, and you adjust the length in such a way that we get into the required aspect ratio, and at the same time see that the length of the fiber is not less than the size of the aggregate. If it is less than the size of the aggregate, so it is not really going to contribute to the matrix, where concrete as a matrix, concrete as a composite I am talking of, but a smaller length still can contribute to your mortar, but it is not going to contribute to the concrete. If you really want to enhance the property of the concrete as a whole, so we need to even see that the contribution of the aggregate to the strength also comes into picture, and that is where the length of the fiber in excess of the length of the aggregate, we have a tremendous contribution to the performance of the fiber reinforced concrete.
So the next question, can palm oil fuel ash also be used to create high strength concrete?
Can
Palm oil fuel ash.
palm oil fuel ash? Yeah, whether the palm oil fuel ash can be used in high strength concrete or not. I would like to tell you at this juncture, we have covered a wide range of supplementary cementing materials. Anything you burn, you get an ash. But what is important is not to use the ash. We need to get a pozzolanic ash. How to get a pozzolanic ash? By burning any material. You take any material, it can be husk, it can be palm oil, or any material you take, you can get the ash. But it is the controlled calcination that plays a very important role. What is this controlled calcination? We need to burn the material for 2 to 2.5 hours at about 600 to 700 degrees centigrade for nearly 3 hours, nearly 3 hours. And later we need to cool the system for about 1 hour. And an average about 4 hours of heating and cooling is what is referred to as the calcination. Then the powder, what you are going to get, the ash, it will be amorphous in nature. Only when the ash is in amorphous nature, it contributes to the strength. Simply by burning, it will not be amorphous. It will be some sort of a, what I can say, crystalline in nature. And it is something like grinding a sand to the fineness of cement and then using the sand as a cement. No, it's not going to contribute. So any ash, whether it is a palm oil ash or any ash, you have to have a calcination process. Even with that calcination process, if your ash is pozzolanic in nature, able to behave like any other supplementary material, yes, that is the best one. I have seen many technical papers from the Malaysian universities being published in construction and building materials, where different types of palm oil ashes and kernel ashes are being used, and they have got very good results. Thank you for the question.
There's one more question. The mixed design shows super plasticizer as 0.5% of CM. I guess CM is cement, not here. Would you please elaborate?
No, the content of the plasticizer, my dear friends, it is always be based on the content of the cement or the content of the cementitious material. So you have seen the mixed design. In fact, in that mixed design, I have mentioned what is the content of the cement, slag, and silica fume. All the three put together. Suppose if it is 500, then 1% of 500 is 5 liters. So if I have mentioned it as 0.5, it is 1.5 liter. So you need to exercise 1.5 liter of hyperplasticizer as 0.5%. That is where 30-40 liters of water will be reducing, and 1.5 liter of hyperplasticizer, you have to use it at the time of mixing to get 1 meter cube of concrete. Otherwise, whatever the concrete you are planning, and accordingly the content of the plasticizer need to be calculated, and we can get the concrete which is highly workable in the laboratory.
The floor is open for any other questions.
If you have any other questions, you can just ask. Maybe 1 or 2 questions I will take up. And otherwise, as I mentioned, you can call me over a phone, you can send email, and I'll be extremely happy to interact with all of you. And we're all in the same teaching domain. So anytime you are welcome to have an interaction with me. Thank you very much, my dear teachers. Again, thanks to all my colleagues who are here, and my HOD is also very much close to me. I take this opportunity to thank my HOD and also my colleagues for giving me the wonderful opportunity. Thank you very much and have a good time.
Very nice.
Thank you, sir.
Thank you, sir.
Very nice.
So thank you, Dr. Nataraja, sir, for the insightful session regarding application of high strength concrete in rigid pavements. Most of the doubts have been answered, and I hope everyone had a very fruitful session. I request all the participants to join us for the next session at 2:15. Without any delay, we'll be beginning.
215.
2:15, sir. Thank you very much.
Break for lunch.
Yes.